Bismillahirrahmanirrahim. So it's not working. Not working. No. No, flash. Okay, Bismillahirrahmanirrahim. So this is a very fundamental talk about the green synthesis of nanoparticle, especially for the people who are not familiar with this area. So let's go quickly. So people started working on nanoparticle preparation, nanotechnology, nanoscience in different areas without having sufficient background about the science and how this scale work when you go to the nanoscale. So it's like the blinds describing the elephants. So each of them describe from their perspective without having enough information. The people who are sitting here in this room, we should all appreciate the Feynman's famous lecture about there is plenty of room at the bottom, because this is kind of the starting point for the nanoscience and later nanotechnology. During his talk, he mentioned many strange phrases, sentences about nanoscience and nanotechnology without mentioning this word. But if you think the scale or the size of the device during Feynman's time and now, so there is a huge difference between them. For example, the computer was like the room, and the human being can walk around this room. But nowadays we have these smart and very highly speed computers. This is the same with the TVs and the ugly transistor, which was provided by Bella in 1947. And nowadays we are very lucky because we have single atom transistor. So in short, nanotechnology includes all of this this scale, especially there is two definition. British definition and the American definition about the scale of the nano, but it doesn't matter. For me, whenever this nanoparticle work, it doesn't matter. So we don't care about this 1 to 100 nanometer at all. But here in this talk, I will be talking about the nanoparticle precisely. So the natural nanoparticle, which was discovered in 1996, was buckyball. By this chemist. So buckyball is basically 60 carbon together, and the diameter of buckyball is only 1 nanometer, and buckyball is the element of the smoke. So in order to have enough information about the buckyball, so it's like the size of the globe is 100 million times bigger than the size of football, and the size of football is 100 million times bigger than the buckyball. So this is the globe. 8.2 billion people living in the globe, while we can put 12 billion components in only 8-inch silicon wafer in our electronic device. So the interaction of light with matter when you go to the nanoscale is a great manner. For example, these are gold nanoparticle, each of them different size, so the interaction of light is different. And I guess this 1 to 100 nanometer comes from this, because when you go to the 100 nanometer, the water will be entirely transparent, although there is a gold nanoparticle inside. But this is not the real case. The real case is nanoparticle has this great surface area per unit volume. For example, if you compare 1 nanometer size granular sugar with a cubic sugar. So cubic sugar has 60 per meter surface area, while the powder sugar has 3 times 10 to the power 9 per meter. In order to understand this, so it's like if you have 1 gram of nanoparticle, it's sufficient to cover 2 tennis court area, each of them 260 meters square. Also, there is another great or important properties, which is most of the atom will be on the surface of the nanoparticle when you go to the nanoscale size, especially when it comes to the quantum dot. So it's, you can say 90% or even 95% of the atom will be on the surface. Here I made a calculation. For example, if you have 1 nanometer radius palladium nanoparticle, so I calculate this by myself. So you can fit like 285 nanometer atoms, in 1 nanometer, which is about 62% of the atom will be on the surface of the nanometer. So normally in our daily life, when things get smaller, they get weaker, but this is not the case with the nano size. So it's like an ant can lift up to 10 times more than their own weight. Also, there is another properties we call quantum confinement, and this is will be dominant when the size of the nanoparticle will be comparable with the de Broglie wavelength. And this is very important, especially for the oxide nanomaterial. So this is the case of the band gap. When you have a band gap, so it's not like a bulk material. In bulk material, you have a fixed band gap. But in nanoscience, the band gap will be function of the size. So we call tuning band gap. So whenever you change the band gap, the size of the nanoparticle, you are changing the band gap precisely. Maybe you ask me why this is important. Well, the most important application is the Q-lead, because we have lead, and then optical lead, and then nowadays we have quantum dots lead, and then the enhancement of the screen, TV screen, computer screen became more important. Now, when it comes to the preparation of nanoparticle, for me, it's not only science, it's science plus art. So it's like Michelangelo said that inside every stone there is a statue, and the task of the sculptor to discover the statue. So it's, for me, it's the same, because for statue you can either start with a big stone and then end up with the statue, or you can start with the sand, mix it with water, and then end up with the statue again. So we call this in nanotechnology bottom-up and top-down approach. So this is the bulk material, and then crushed, then you end up with the nanoparticle, or you start with the atom, which is most likely our method for green synthesis method. So we start with the atom, and then we end up with the nanoparticle. But the problem is we have three different areas in order to prepare nanoparticle. So when you start with a physical method, there are some drawbacks such as high pressure, expensive method, time consuming, and so on. When you go to the chemical method, so you can provide unstable nanoparticle, which is problematic, and also toxic nanomaterial. You should use toxic material, expensive, and so on. But when it comes to the biological, or you can say green method, so it's basically low temperature, green procedure, inexpensive, one pot, eco-friendly, and the most important is stability. So this is the clock that we are working on it. So in this clock, we started with roots, flower, leaf, fruit, and ionic liquid. But there are many things. We should finish this clock sooner or later, if you have enough time and enough PhD and master students. So why we are focusing on the green synthesis method? Well, in green synthesis method we have minimal waste and renewable, cost-effective, low risk eco-friendly, abundance, and non-toxicity is the most important one. So also there are many factors affecting the size and morphology of the nanoparticles, such as calcination temperature, pH value, reaction time, reaction temperature, precursor concentration, extract concentration, and so on. But the most important thing is inside this plant there are natural reducing agent, natural stabilizing, natural capping. This is a non-toxic material. These are cheap material. These are suitable for sensitizing many different types of nanoparticles. So here we are focusing on the stabilizing and capping and reducing agent. We need a reducing agent. In fact, in order to reduce the metal ion inside, because we start with the salt and then mix it with deionized water, so we have ion. Then we need a reducing agent to change this ion to the atom. And then the atom comes together by nucleation process because we put this on the heater. And then after, we need something else, which is the preventing nanoparticle for agglomeration we call capping agent. And then later, we need a stabilizing agent because stability is the most important parameter, as I mentioned before. So inside the plant extract, the gut puts all of these important things for us. For example, stabilizing agent and capping agent, reducing agent. And the sharing factor between this phytochemical we call is the OH group, which is the most important parameter here. So the most important thing is you start with the stabilizing agent, capping agent, and stabilizing agent. Okay, in order to have enough information, it's like when you heat the pots, so you end up with the corn. But this corn you cannot eat it unless you add, for example, salt. So this is capping agent, and then you have to pack it, and this is the stabilizing agent. But when you start with any plant, it's better to analyze the plant extract before wasting your time, wasting this chemical. So you are free to utilize these techniques, HPLC, GC-mass, LC-mass, FTIR, UV, and so on. So when we analyze this by, for example, GC-mass, so we found all of this phytochemical, but okay, the question is, which phytochemical exactly doing this for me? So in this case, it's better to do such as some quantitative, let's say, quantitative analysis. For example, UV tells you the dominant phytochemical. So it's very important actually, because the size of this phytochemical responding to the different peaks of the UV light. But the second question is, okay, what about the capping, reducing the things that I mentioned? Well, the FTIR will give you this. So reducing agent is basically this OH white or big group, and then capping agent, and then stabilizing agent. This is all by using the phytochemical. So, so the thing that we started, okay, we can produce nanoparticle, but the question is how this happened. So what is the mechanism for producing nanoparticle actually? So we started with, for example, first we started with the metallic nanoparticle, and then we provide a very dense research article about the metallic nanoparticle, and this became the base for many researchers that this is the scenario that we provide for producing nanoparticle in terms of the phytochemical and the reducing agent, the inoculation process, and growth and stabilizing. Then later we provide another one for the oxide material. So this is for zinc oxide material using parsley. Parsley is our hero in the plant extract because the parsley is important. Now, in order to know the impact of your scenarios, so it's better to go to this. These books about the scenarios that have been used by our groups. So all of these books, when it comes to the mechanism of formation, nanoparticle dimension, dimension or mechanism, which is great. Actually, these books are very important, and the people using these books everywhere. So that's why GPS listed me in the top nanotechnologist, and then this is the certificate, and this is the Stanford University, and so on, for 2023 and so on. Then we made another study to compare between the chemical and the green method. So we provide two research about the silicon dioxide and magnetite in order to compare, in order to tell people what is the real difference between the chemical method and the green method, actually. And then about the fresh and dry plant extract, also there's a dense research about, okay, whenever you use dry plant extract, you lose some important phytochemical, which is affect your nanoparticle. So far, we have more than 150 articles in this regard, but our main focus are on this project. Water purification is our main project, and then heat generation, solar cell efficiency enhancement, enhancing building material, antibacterial, antimicrobial, anti-cancer. Okay, we started with this new project here. It's a carbon dioxide capture, a nanorod, a nanodentistry, nano in 3D printing, and nano in agriculture. So when it comes to the water, so water it contains the heavy metal, toxic dye, bacteria, virus, colloidal particle, and pharmaceutical, and so on. So we started with this research about this water purification. First we started with different dyes, and then reducing chromium 6 to chromium 3. So we succeeded within a very short time. Then later we comes to the different nanoparticle. For example, nickel oxide nanoparticle from Halabja pomegranate. So this is locally grown plant extract. So we could reduce the time from this 7 to 5 minutes to 37 minutes. So this is zinc oxide, and this is coating this nanoparticle on bentonite, and then we reuse it for water purification for different dyes such as conglomerate, rhodamide, and methylene blue, and so on. And this is comparing between ionic liquid and green synthesis, because in green synthesis sometimes we have agglomeration problem, which is problematic. So this affects your stability. The stability of the nanoparticle is strongly linked with the agglomeration. So we could overlap this problem. Look at the green synthesis morphology, and look at the ionic liquid. So now our nanoparticle is much better. And then in terms of the antibacterial, antimicrobial, also it's more efficient. So, and then we made a very great research on the water treatment by using Fe3O4 nanoparticles. So we collect all of the articles in the world, and then we found the gap. Actually, where is the gap? So what we can do for this? And later we started with nickel ion degradation. And the second project is the heat generation inside water. So this, we are pioneering this one. So we add nanoparticle inside water, and then we eliminate it with light, and then due to the surface plasma resonance, we could provide heat inside water. So then we change it from metallic to magnetite nanoparticle, and then we increase the temperature of the water precisely. So all of this study are on the heat generation. So carbon dioxide capture is a new project. Actually, it just started with a group from Turkey. So this is basically adding the carbon dioxide inside bed machine instead of nitrogen, and then put nanoparticle, and then we select 3 different types of nanoparticle, and we realize that zinc oxide nanoparticle is the hero in this regard. And then for enhancing solar cell efficiency, actually we started with some simulation, and later we changed it to the research. So either by using plant extract or ionic liquid with Dr. Abu Bakr is also here. So these are the very, very fundamental research, because normally the solar cell has this problem. So we started with the polycrystalline silicon solar cell, the commercial one, the best one, and then we measure the efficiency, and then later we add this nanoparticle in order to enhance the nanoparticle with different, of course, size, different nanoparticle, and so on. In terms of the thin film preparation, we also prepared many different types of thin film in order to absorb UV light. So here we prepared a thin film for absorbing gamma ray, which is a very problematic here. So you start with the transparent glass coated with lead oxide nanoparticle, and you can attenuate about 70% of the gamma ray, which is great. That's why we reach AS omega here. Then in terms of the in terms of the microwave, so microwave also problematic. So people concerned about microwave, because microwave can penetrate our body and make this polarization, and the polarization make cell displacement, and the cell displacement is equal to cancer. So we try to coat the gate of the microwave with Fe3O4 nanoparticle, and then we succeed in this regard. In terms of the enhancing building material with people from engineering, so we started with adding different types of nanoparticle in order to enhance different types of building material, unless we reach the limit of the construction building material. To be honest, reaching this level is not easy unless you provide this kind of great contribution here. In terms of the biological application, so we started with the killing unwanted bacteria. For example, in this study here, we grow a bacteria on the sheep liver, and then we add zinc oxide nanoparticle, and within a very short time, the zinc oxide nanoparticle kill all of this bacteria. So we started with anti-cancer application here. So this is also our green synthesis nanoparticle, and then people from biology started using this nanoparticle for anti-cancer properties. In terms of different adding coating different masks during the corona time, so we have nice projects. I'm not going into the detail for the nanorod, because Dr. Samir will present a very intensive presentation about nanorod. Just I say that we are the pioneer in this group. So we produced the first green synthesis nanorod for the first time. And then in terms of nanofluid, we have many articles in this regard. Because of the time, I'm going faster. Okay, in terms of the hydroxyapatite, producing different types hydroxyapatite for both tooth application or bone regeneration. So we are working on this regard. So let me go faster. So in field emission with Jordan group, also we started with this one. We have several review articles. This is my published book. And thank you so much.
Thank you very much for the nice talk. Yes, thank you. I think we don't have time for a question, but we can make maybe one question. Yes, please.
Yeah. Yes. 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 Well, it's not expensive. It's like time consuming, to be honest. Because okay, I always tell this with the person tell this to my friends that if you start from 9 a.m. until 5 p.m., you can produce 2 grams of nanoparticle. 2 grams of nanoparticle. So this is the best we can do. But this is the end of the research. So we can we fixed, we solved a problem for agglomeration. Okay? So now we think always, we are thinking about this producing mass production of nanoparticle is one of the problems, yes, we have. And there is one also, which is the toxicity. Okay, we are not 100% sure that our nanoparticles are safe. So toxicity is also, yeah. Thank you so much. So Ahmed?
Yes. Okay, thank you again. And thank you. Let's thank the speaker. We'll go to the next talk with Dr. Muhammad Nadeem. Muhammad Nadeem. Yes, but it's not ready, right? We will take it from yes. Okay, so welcome the speaker, Dr. Muhammad Nadeem Abbas, University of Baghdad, and his talk is from Light to Logic on chip photonics and optical computing. Yes, please.
Thank you very much. Today I will talk from light to logic on chip photonics and optical computing. So today I will discuss the fascinating revolution in computing, the shift from photonic to electronic, from electronic to photonic and plasmonic technologies, and how light can be used not only for communication, but also for logic process on a chip. So, as we know from Moore's law, that the density of transistors doubled every roughly 2 years, but because the electronic device approaching the fundamental limit of physical limit and thermal limit, therefore there's a deviation from the growth of data from what the Moore's law states. Therefore, there's a problem and we need a solution for this problem. So one of the best solutions is to use photonic integrated circuit instead of using conventional integrated circuit. So, the elements of photonic integrated circuit can be done like the light source, waveguide of light, modulation, photo detections, low cost assembly. But what the most here, the arithmetic logic units. So we need to use a photonic or all optical arithmetic logic units. So therefore we need to build all optical logic gates to use this photonic integrated circuit. So our ultimate dream to build a complete miniature photonic integrated circuit. So in order to shift from conventional integrated circuits or conventional CPU to the all optical CPU, so we need to build all optical arithmetic logic units. So let's first to compare between the conventional integrated circuit and photonic integrated circuit. For the conventional integrated circuit, it's already approached its fundamental speed and bandwidth. But for the photonic integrated circuit, high speed and bandwidth capacity can be done for this mode. The advantage in using the conventional integrated circuit can reach to the nanoscale, so there's no diffraction limit. But the problem with photonic integrated circuit, there is a diffraction limit. So as we know, the light cannot be confined in size smaller than its wavelength. So how to solve this problem? The solution of this problem, we can use a surface plus one polariton, which is the interaction between the photons and electrons as the interface between the metal and the electric. So we can bridge between the advantages of two criteria here, the high speed, you can get high speed and bandwidth capacity with nanoscale dimensions. Therefore, in order to obtain the all optical arithmetic logic units, so we need first build all optical logic gates. So here, by utilizing the silver